Feel better at your place? Sorry to this location.
Yeah, the back and front are rolls away.
Yeah. All right. All right, everyone, we are now starting with the lecture, so please get seated, turn off the Zoom, and yeah, please don't talk to each other right now. Okay, so last time we had stopped with the best rank K approximation of a matrix, and I want to go over this again because I did it in a little bit of rushed way, and I also did some mistakes along the way. So right, let's go over this again. So here we are going to use our SVD decomposition of a matrix to find another matrix which has a rank of a given number, K. We give that number, and it is going to approximate the matrix, original matrix A, meaning that is going to we set this kind of vaguely, but it's going to have all the characteristics of the matrix. So let me go over the dimension of each of the matrices because I did that wrong last time. So we are going to have original matrix was of size n times d. I'm going to omit the set of real numbers just for the simplicity. And our new matrix UK is going to be of the size n times k. This means that we are going to take from our original matrix U, which was n times n square matrix, we are going to take only the first k columns. All right, so we are taking first k columns. Then from our matrix S of singular values, we are going to take only the first k. So our matrix SK is going to be of size k times k. And then from our matrix V transpose, we are going to take only the first k rows. So we are going to have VK element k times D. Original matrix V was D times D matrix. And we are going to multiply these matrices UK, SK, and VK transpose to get our matrix AK. So UK, SK, VK transpose, very similar to how we could decompose the original matrix A to the product of U, S, and V transpose. And this matrix is also going to be n times D matrix, but it's going to have a rank of K. So basically what is happening here is the same thing that happened when we did PCA. We are finding these most important directions, and we are projecting our data to those directions. So when we get this matrix AK, we have used only these first k vectors in our matrix U in only first k right singular vectors. And that's how we have made use of only the first k important directions. All right, so when I was showing you how we can basically reconstruct an image using some of the columns of the original matrix, initially we had this image or another cat, and the size of this image is approximately 3,000 times 4,000 pixels. And then we did exactly this kind of multiplication where we took the first, here we use R instead of K, don't like that to confuse you, I change it in the images, but not in the code. We do this multiplication of only the sub-matrices of U and V and S. And then depending on the number of directions we are choosing, we can get, with less of them, we are going to get worse reconstruction of the matrix, of course, but more we increase our K, we can get better approximation. So here with K equals 75, we have used only the first 75 columns in our matrix U that had 3,000 columns. So only with 75 of them, we managed to retrieve these important directions. And that's the point, that in your high dimensional data, you have a few of important directions that can reconstruct your data, that has all the information about the structure and semantics of your data set. And that's why the dimensionality reduction is a useful thing, because if you can represent something with less of everything, then you don't have those issues we have talked about last time, such as multicollinearity. And of course, efficiency is always in our mind. All right, and as always, none of these things have to be, coded from scratch. I mean, you could have seen now that it's very easy to also do this matrix multiplication, but you can also use truncated SVD from scikit-learn as always. Now, I did say something that might have kind of sparked your curiosity, and that's that with this SVD approach and with this taking first k columns and doing the rest of the multiplication, we are basically doing what we have done with PCA. And a totally reasonable question then could be, okay, what is the point then if we have PCA, and why would we like to do the same thing? Are these things the same, and so on? And you would be right to say that these two things are achieving the same thing. We are finding these most important directions and we are projecting to them, but the way we go about it is slightly different. So with SVD, we are going to have our centered data matrix, and we are going to directly apply SVD to this data matrix. With PCA, we are going to use eigendecomposition, and we are going to not apply eigendecomposition directly to our data matrix. We are going to apply it to that product of the data matrix with its transpose. So there are these slight differences. And you might wonder, okay, which one of these, why do we have these differences? Is this just we came to the same thing with different mathematical derivation? Is this exactly the same and I don't need to worry about it? And there you would need to know that these things are, one of these things might be better in certain situations. So first of all, I want to point you to this tutorial on PCA. And here you can find very formal derivation of why these two things are mathematically connected. So if you are interested in that, go to this tutorial, check it out. And going back to my question of when do we want to use SVD to compare to PCA, it turns out that SVD is numerically more practical than PCA in certain situations. So for example, there is this example of this Lauchley matrix, which has very stable singular value decomposition. But if you would compute the product of this matrix with its transpose, you can get something that's not really nice. So there are examples of matrices where eigendecomposition or, not eigendecomposition, but this product, the necessity to compute it is not great for us. SVD is more applicable to sparse matrices because of all the stuff that has been implemented around it. And there is also the question of centering sparse data that one needs to think about. And then there is a little discussion here that I want to point you to the differences in the implementations of PCA and truncated SVD. There are differences between these two things. So if you are interested to know a little bit more about this, I recommend reading this Stack Exchange post about it, where you can learn more about where exactly these things are implemented and how that can impact your own problem. So while PCA and SVD are super connected, they are mathematically slightly different, and also their implementations are slightly different. So be aware of these differences, and whatever is the problem you're working with, think which one of these is better for your own problem. Okay, any questions about SVD and PCA? Okay, was there a question? No, okay. So we are going to now move to another topic, and this is a random projection. And I want to offer you two ways to motivate why we are now going into this another method for dimensionality reduction. So we are still working with methods where we have our high dimensional data, even want to project it to our lower dimensional data. And we are going to talk about this topic the entirety of the next week as well. So one typical motivation for introducing random projection is to say that, well, PCA and SVD are actually very time consuming. The complexity is square in the dimension, in the number of features we have of our data, and is very, very time inefficient in terms of the parameter K we are choosing as well. So it is not the most efficient method to work with. Yeah. It's the size of the lower dimensional space.
Okay.
Yeah. All right. So another reason why SVD and PCA are another limitation they have is the formulation of minimizing the average squared norm between the point and this projection. So what happens is, just a moment, let me finish this thought. So if what we are caring about when we do this approach, when we are minimizing this objective, is that we are just care about the average case. We don't care about the worst case. And that means that if you have a presence of one outlier, that can kind of mess up your minimization as well. So PCA and SVD are sensitive to the outlier just by the fact that we have started with minimizing the average error. You had a question?
Yeah, I was gonna ask about how you choose what a reasonable K is if you don't have like CAD images that you can visually look at.
Yeah, so again, that's a hyperparameter. You don't know the answer to this question. You are going to have your some kind of data you can look at and decide what is the reasonable number of K. So if you had a downstream evaluation, you're doing dimensionality reduction to do something else, and you can measure that something else. You would tweak, try different values of K and see what is the downstream impact. And you would pick the one that works the best on the development data and evaluate it on the test
But it
data.
wouldn't have to be like downstream. There's no way of directly evaluating it.
Think about someone evaluate that you do like 30 jobs for costs or any sort of inequality qualification.
I am not familiar with that, so you might be right that exists. I don't know what exactly are you referring to. These are mathematicians who have developed many things, so I don't know what exactly is the thing you are mentioning here. For example, with this image stuff as well, we now could the image we have reconstructed is of the same size as the one we started with. So you can just measure the difference between them. You have matrix norms. So you can measure the difference between your original one and the reconstructed one. And you might see that the one which is reconstructed has a smaller norm with respect to the one you are trying to reconstruct, if that makes sense. But yeah, I don't know a ton what people are actually doing here in terms of besides using this kind of for visualization. So sometimes you'll just see stuff which are visually appealing, but I personally don't recommend doing that because it seems like a slippery slope to cherry pick things that work for yourself. Okay, so let's then move on. So I said we are going to now introduce one new dimensionality reduction technique called random projection. And I said this is one way people will motivate it with. I would rather think about this as just another method that serves different purpose. So with SVD, as I just told, we can essentially promise that you tell me what dimension you want to live in, and I'll give you the best possible embedding, but best is defined on average. We are minimizing the total error of true similarity versus projected similarity. Remember that equation where we had a sum of squared errors, and we were looking for the one that minimizes the norm between the point and its projection. So you're thinking about what happens on average, and we have seen at the end that indeed, when we do SVD, the way we have put those singular values in our matrix of singular values, we have put those that are the largest in the first k values, and then that implies that all the singular values from the position k plus 1 to the end are as small as possible, just because we put the larger ones before and we are putting them in an order. And we have seen that the sum of singular values from k plus 1 is exactly the sum of squared errors. So we indeed found with SVD the best possible case. And I want you to think about random projections as a thing that solves something else. And that's, if you give me the error you want, I will give you a low dimensional space that preserves pairwise distances of your points up to that error. So you are thinking more about the worst case possible, because you are guaranteeing that every single one of your pairs in the original space will in your low dimensional space be equally distance apart. So to me, this means that with random projection, you can solve or think about slightly different problems than necessarily what you are interested with SVD. But at the same time, random projection will be more time efficient. And because of this worst case pairwise guarantee, it's going to also be less sensitive to outliers. Okay, so let's get into random projection. The basis of random projection is something called Johnson-Lindenstrauss lemma. And this is basically the lemma that says more formally what is described here in the previous slide, where I said you are going to make a low dimensional projection that will preserve all pairwise distances. So in more mathy way, that means we are going to define some epsilon that will be our error as always, and that's going to be a number between 0 and 1. You can think about it also as a percentage of how many times you will not guarantee those pairwise distances. You will have a set of endpoints. Each one of your endpoints is going to live in a d-dimensional space. And what Johnson-Lindenstrauss lemma is saying is that you can find, you will be able to pick number k, which is still the dimension of our lower dimensional space. And it's going to be given by this formula here. Sometimes you will see different forms of this formula, just depending on how the bounds are derived, but all of them are going to have either natural logarithm or logarithm in the base of 10 of the number of examples n we have in above the fraction line, and below fraction line, you will always have the squared error. So although you might see slightly different variations of this, these two things will always be there. All right, so given the error, given your set of n d-dimensional points, and given this size of low dimensional space, there is guaranteed to exist a mapping from your high dimensional to your low dimensional space, such that, and then this equation says that you are going to preserve the pairwise distances between every single point you have in your data. All right, questions about any of this so far? Okay, so this is, I think, pretty neat result, right? It's very nice. And I think it's nicer when you read it like this and don't really think about what are the potential values of K. In a previous sentence and all the sentences before, I said a set of points in a high dimensional space can be embedded in lower dimensional space such that you can preserve these pairwise distances. But if we read this whole lemma, nowhere here is explicitly said that the original dimension of our space has to be large. So why is it important that that the dimension is large? And that just comes from the fact of how we define k. So let's say you have epsilon of 1%, or which is 1.1. So this is how much error you allow. This means that your epsilon square is going to be 0.0001, and your 1 over epsilon square is going to be 1000, right? Okay, let's see when ln is going to be larger than, let's say, 1. It turns out if you have at least 3 points in your data set, then the ln is going to be larger than 1. Which means that together, when we use this formula over here, that means that your k for these values is going to be larger than 8000. So what has happened here, and this is for very small values of n, and of course we are working with data sets where we have lots of points. So what becomes clear here is that k many times has to be actually very large. So this whole problem and this whole method makes sense only if your original dimension d is really large. Think about 100,000 dimensional space. Then you can project it to something which is, let's say, of order 10,000, and that's good because decreasing from 100,000 to 10,000 is nice. But if you didn't have more than 10,000 dimensions to start with, then probably this won't make any sense for you to do. Is that clear? Okay, so nice thing is that since this is really important, in scikit-learn you do have a function that will tell you what is the minimal dimension, what is minimal k you need for a given number of samples and a given number of the error. So you can just plug in this function the number of samples you have, epsilon you want to achieve. You will get some min k out of this, and then you can see, well, does this make sense for my problem, given that I have certain number of features? And from there, you can conclude whether this makes sense for you. This plot also illustrates how for smaller values, so this is here, we have epsilon. Smaller the epsilon is, so smaller the error, you will of course need a larger k. And that's obvious because the formula for k includes 1 over epsilon square. So smaller the 1 over epsilon square is larger, smaller epsilon is larger, 1 over epsilon square is going to be. I'm not connecting it to overfitting. I'm saying it literally won't make sense to apply this method because your method, this is based on this lemma, and this lemma says that your k is going to be this number. So this holds, this property that you are going to preserve pairwise similarities hold for this specific value of k. So if you have dimension d, original number of features, that not sufficiently high, it's not higher, even higher than your number of k that you can project to, then you can't use this method. Yeah. Or, I mean, oops, sorry, go ahead.
How often will you work with data sets that have like with 8,000?
Yeah, so there are definitely data sets with features that have more than 8,000. So in homework, I will give you one data set that has over 40,000 features. That comes from like a book corpus. So don't worry, there are problems which have this many features. We have last time mentioned, for example, what if you have n weather stations, that's each one of your points, and then each dimension, each feature is one measurement in time. you can measure and measure and measure, and you have very long history, so that can be really long. So it really depends what you're doing, but believe me, there are problems which have many features. Yeah. Okay, what else do we see here? We see that with more samples, also each one of these lines is for a certain number of samples, and we had ln of the number of samples. So of course, if you have more samples, the natural logarithm will be larger, and that will also mean that you need larger k. The nice thing is that nothing really, in the formula, we don't have explicitly the number of dimensions. So it's really just these two things you kind of need to think about. What is the error you are allowing? How many samples you have? Okay, any questions about this? Yep.
What is the idea of why this thing works? So, like, how, if you have the requirement, why the error will be low? Like, what is the method which is being used and then to prove that it gets lower error when you take such a construction?
I don't get your question. Can you repeat it, please?
If such constraints are satisfied, you take such k, and then so I just want to know what's the proof why the error will be very less. Like, what
Are you
to get the space, low dimension space?
okay? So, are you asking about the proof of the lemma or about the construction of the mapping mu?
Yeah, proof of the construction, how to get the space.
Yeah. So I pointed you here to where you can read the entire proof. It is proved by construction. It goes by, originally said you need to orthogonal unit vectors. And from those unit vectors, you're just going to keep projecting your data to it. And this is going to then satisfy this inequality. Later on, it is shown that orthogonality is actually not even important. You just need random unit vectors, and you will need to project your data to it, and it's going to work. It's a little mind-blowing, and I will talk about it in, I think, maybe even next slide. Let me first go over the algorithm, and then we'll talk a little bit about why does this work.
So with SVD and PCA, it was like features that already existed, and it was like the most important ones that it was returning. For this, is it like coming up with new ones, or like what does it mean when it says like a low dimensional space? Like, is the space features that already exist, or is it coming up with new features to define the space?
Even with SVD, you don't really know what those features are, and you are projecting them to a low dimensional space. And it turns out that you have kind of removed the noise, right? Remove all the features that can be predicted from other features in your data. Here, the motivation isn't about projecting it to using these important directions. It's just finding the subspace where you will preserve these distances. So we are not talking about the most important directions anymore. But obviously, if you have now good representation of your original data in lower dimension, where you can still have some information that can predict what were the original distances between the points, that low dimensional data has captured something about the structure of the original data. Okay, so let's go over, oh, sorry, yeah.
Each line of the data set or each data point into a feature and then remembering to take. To gain dimensionalizing high
I don't get your question. I'm sorry. Can you rephrase it?
I mean, you need more than 80,000 dimensions. So if my data set is, does not have that much
Mhm.
dimensions, I turn each, line of the data set or each data point into a feature. I consider data points as features and then leverage it.
Yeah, I think we are overloading terms now. So your data point, each dimension of your data point is a feature. The whole data, and you are trying to do something with your data points. Now, if you would say one of my data points is a feature, that's not the same problem anymore. So let's go back to weather stations, and you'll have now in a vector of, let's say, 100,000 measurements from that weather station. What you are suggesting is to now say that that's the whole vector is one feature, but feature of what? And kind of, I don't see how you can, basically what I don't see is how you can transform your original problem to what thing you are describing and still solve the same problem. I don't think that is possible. But maybe I missed something, and please correct me later on if true. Okay, so the point is, if this is not satisfied, it's not the end of the world because you have other techniques, namely PCA. And we said PCA's problem is that it's slow when we have large dimensions and so on. But if you don't have that problem, then you will just use PCA and it's going to be probably fine unless you have some really bad outliers. And that's the only thing you will need to maybe additionally think of. So the fact that this is not necessarily satisfied is not the end of the world. You still have other techniques, maybe not the perfect ones. Maybe you really want to preserve those every single one of the distances, but you will still be able to do something. So my bigger point here is not that you should kind of bend your data such that it fits this problem, rather that do not use this thing if you don't have this number of dimensions satisfied.
Could we use the pairwise distances with like SVD or PCA to quantify what a good K would be? Like is there like an elbow or something for that?
As far as I know, everything about K is just hyperparameter search. So I don't know anything else about choosing K than doing hyperparameter search. So still the same answer as before. That doesn't mean that this doesn't exist, but as far as I know, and
But you like want to care about the pairwise distance in the other two?
in random projection, yeah,
No, in PCA or SVD, you wouldn't care about the pairwise distance?
It's not that you don't care, you're just saying on average, I want them to be set, kind of. You're saying on average, I want my projection and my original point to be close to each other. That will probably also on an average kind of preserve the similarities of your points, but it's not explicitly embedded in the algorithm and you have no guarantees about it. So yeah, let's not just now try to, think too much about how to bend problems here to the issues there, because we'll never get to the algorithm itself. So SVD, PCA did one thing. Now we are focusing on the problem of pairwise distances, and we have a technique for it when we have certain number of dimensions. And the technique is extremely simple. So you will have your data matrix A. You will just construct K random d-dimensional unit vectors, UI to UK. And this comes from the proof. So the proof of the lemma had said, construct these vectors. Originally, it had also said you need orthogonal vectors, but then later on that requirement was lifted. So this thing comes from the original proof. And then for every single one of your points, which is one row in this data matrix, you are going to make a dot product with that vector with every single one of your unit vectors, which will give you, because it's a scalar product, with every scalar product will give you just one number. So that number here, we'll call it QI. We are going to collect them for every single of these unit vectors we use. and we are going to put them in a sequence, and that's going to be mapped representation of our original point AI. That's all we do. There is, of course, a compact way to write this, but I want to stop here because I think it's better to immediately say why does this work? It's kind of very, very simple. Why do you just need unit vectors, not even orthogonal vectors, to map your stuff in a k-dimensional space? Because if you had k unit orthogonal vectors, then you would have a basis, as we have learned last time, for a k-dimensional space. So if you did exactly what we have done, a scalar product with each one of these orthogonal vectors, that would kind of make a sense as a projection of the vector onto some space, k-dimensional subspace. But here, we don't even require they are orthogonal. And the fact that this works comes from the property of, again, very large, very high dimensional spaces, where if you have, I will read this out, in high dimensions, exponentially large numbers of randomly and independently chosen vectors from certain distribution, this is not super important, are almost orthogonal. So you pick two vectors from very high dimensional space randomly, they will, with very high probability, their scalar product will be very, very close to zero. And we know that all orthogonal vectors have scalar product of exactly zero. So here, by saying almost orthogonal, we mean that their scalar products are extremely small, and this will happen with the probability close to 1, which means that, okay, if you are now randomly drawing k unit vectors from your high dimensional space, they will behave like orthogonal vectors, and they can then be a basis for a k-dimensional space. And therefore, when we are projecting to these vectors, we are doing a projection to a k-dimensional space, as we have learned it last time. This is why all of this kind of makes sense. So going back to the algorithm, here I said I have a for loop where we go over every point. A compact way of writing that is that from these vectors ui to uk, you just produce a matrix U that has each one of these vectors as column. And then all you need to do is a product between matrices A and U, and then each one of these rows in the new matrix you have produced is going to be the exact mapping we have seen there before. It's just a more compact way of writing, and then of course, how you would go about implementing something like this. Okay, let me see what else I want to talk about. Okay, so we are very close to not having any time left, and what we are going to talk about then next is how to pick these random vectors. We are going to pick them either from Gaussian random distribution. We are going to also define some sparse distribution. These are going to be your standard choices, and then we are just going to wrap up with like one or the other when to choose them. But I will leave that for the next time, because I realize when I try to rush, I just make mistakes. So see you on Monday.